The goal of physics is to predict the future given the present descriptions. This is an advanced physics channel, and here we discuss classical mechanics, quantum mechanics, cosmology, relativity, and many more. We'll start off with classical mechanics, for that matter, motion, which is the basis of the physics as a field. Now, motion has been grouped into two. We have kinematics and we have dynamics. Kinematics asks the question, where is an object? What is its velocity? What is its acceleration? But it doesn't ask the question, what caused the motion? Dynamics asks the question, what caused the velocity, the acceleration, etc. of an object? So here we don't study the cause, but here we study the cause of the motion. There are three kinematic equations put forward by Isaac Newton that can be used to predict the position, the velocity, and the acceleration, as well as the displacement of an object. So the motion parameters are position. In one dimension, we denote that by, say, x. We have displacement, the change in position, that is denoted by delta x. We have velocity v, which is the change in the position with respect to time, dx dt. Then we have acceleration, which is the change in the velocity with time, or the change in the position with respect to time, but here it is 2 times. So the change in position is also subjected to derivative with respect to time. So the second derivative of the position with respect to time is the acceleration. The three equations put forward by Newton are established based on the fact that many motions that we come across in the universe, that is in space-time, have constant acceleration. For instance, close to the Earth's surface, the acceleration of all objects is g, 9.8 meters per second squared. That is a constant acceleration. If you're also in a car, sometimes you change your velocity with equal intervals in equal times. Now, if the acceleration is a constant, then the three equations are very good at predicting the future parameters that we have here. Let's begin with the position function. That is the first kinematic equation. Now, the position function, when subjected to second derivative, will give you the acceleration. And if the acceleration is a constant, that means the position function is a function whose second derivative is a constant. The function that comes in mind is a quadratic function. So meaning the position function as a function of time is equal to a quadratic equation of the form, say, at squared plus bt plus c. It is the same as ax squared plus bs plus c. But since it is a function of time, in place of x we put a t. So we are taking the second derivative of the position function. The first derivative, dx dt, which is the velocity as a function of time, is equal to first derivative of this will give us 2at plus first derivative of this will give us b. The derivative of this constant is 0. Then we take the second derivative, which is equal to the acceleration, which is equal to dv dt, will be equal to, the derivative of this will give us 2a. The derivative of b will be 0. We needed a function whose second derivative will give us a constant a. But here we are getting 2a, meaning we have to modify this quadratic so that the second derivative will give us a constant a. For that matter, we put a half here. If you do that, that means the first derivative, this 2 will vanish. And here the second derivative, this 2 will also vanish. And you have your second a. So the position of every object in space and in time, if the speeds are not so comparable to the speed of light, is such that it is a function of t of the form half at squared plus bt plus c. The a has been established to be the constant acceleration of the object. So we are left with the constant b and c. What are they? Now to get b, let's come to the velocity function. Now at t is equal to 0, now v of t, that is v of 0 here, will be equal to, this will be 0, will be equal to b. So b is nothing but the initial velocity of the object. That is the velocity of the object at time 0. Now we are left with c. What is c? Now x of 0, that is if we put 0 here, it's actually going to be c. So c is also nothing but the initial position of the object. So having established this, then we have x as a function of time is equal to half a t squared. This is a constant acceleration plus b. What is b? B is a velocity at time 0. Let's call that u, preferably u. So ut plus c. C is the position at time 0. And let's call that x naught. So rearranging our position function as a function of time is equal to the initial position plus ut plus half at squared. Now this equation is the first of the 3 kinematic equations used to predict the motion parameters of every object, derived for objects with a constant change in velocity or with a constant acceleration. Let's show the second equation. The second equation is this one, which says that the final velocity of every object as a function of time is equal to at, where a is the acceleration, b is the initial velocity. So it is going to be u plus at. So for every object with a constant change in velocity, you can predict the final velocity knowing the change in velocity and the initial velocity, which evolves sort of in time. Now with the third equation, you make t the subject here and put it over here. And if you're able to do that, you sort of arrive at this equation: v squared is equal to u squared then plus 2as. That is delta x. That is the third kinematic equation. Just make t the subject here and put it here, and you get v squared is equal to u squared plus 2a delta x. The delta x will be obtained from the fact that x of t minus x naught will give you a delta x. There is another way to show the third kinematic equation. Let me show you that. The third kinematic equation can be shown given that the average velocity of every object is delta x over delta t. Now, is also equal to the final velocity plus the initial velocity over 2. What do we mean by average velocity? It's by summing two velocities and dividing by 2, or taking the entire distance or displacement of an object and dividing by the total time. Now, making the displacement the subject, delta x is equal to v plus u over 2 times delta t. Now, this delta t is the same as t, this t in all these equations. But from this equation, what is t? So delta x is equal to v plus u over 2 times delta t. Now, delta t in this equation is v minus u all over a. That is, if you make t the subject here, it's going to be v minus u over a. And we expand the bracket. If you do that, then we have delta x is equal to, what is v plus u times v minus u? You have v squared minus u squared. That's a difference of 2 squares, and all over 2a. So from here, you have v squared is equal to u squared as written over here. So all that you need to do is that the average velocity can be written in 2 ways: total displacement over total time, or summing the final velocity and the initial velocity and then dividing by 2. And having done that, the delta t, you just make t the subject here, put it back into the equation, and then you expand the bracket. There is a third way I'll show you. The third way to prove the third kinematic equation is using calculus. Now, dv dt is equal to a. Now, this equation is a fact that the first derivative of velocity with time is a. Now, we can choose to multiply both sides by v. So here by v and here by v. And if you do that, this derivative can be written as the derivative of v squared over 2 and this derivative here is the same as this derivative. Now, in calculus, the derivative of v squared over 2 with respect to time is you differentiating the outer. So the outer will be 2v over 2, which will give you v, this v. And then the inner will give you dv dt, which is this one. So this derivative and this are the same, is equal to a. And let's multiply both sides by dt. So the v squared over 2 is equal to av dt. Multiply here by dt, here by dt. We are told in mathematics never to multiply through by dt, but you can. You can't, because between 2 points, if there is an infinitesimal change in time with a constant acceleration, then multiplying through by dt, you can cancel out. This dt is not 0. If it were 0, then you cannot cancel out. Though it's infinitesimal, but it is not 0. You can cancel out. Now, this quantity here, v dt, is a dx. Velocity times time is a displacement. So then you have dv squared over 2 is equal to a dx. And let's integrate both sides. We are integrating this quantity from u, which is the initial velocity, to v, the final velocity. And this integral, this a is a constant, we take it out. So we are integrating this from an initial position x0 to a final position x. And if you do that, the integral of this is v squared over 2, integrated from u to v, and is equal to the integral of a dx will be a out times x, integrated from x0 to x. Now this integral will give us v squared over 2 minus u squared over 2, that is only here, is equal to a times, you have this x minus x0. And if you multiply through by 2, you have v squared minus u squared is equal to 2a. And this quantity is delta x. Then making v squared the subject here, v squared is equal to u squared, then plus 2a delta x. Sure. So we've shown this equation in 3 ways. 1, by making t the subject here and slotting it into this equation. 2, by making use of average velocity. Then 3, by making use of calculus. Typical example of a problem that we can meet in 1D kinematic motion is that a man accidentally falls from a vertical tower of height 10 meters. And the question goes, at what time does he hit the ground, given that he was not pushed? Now, this is a problem set up in such a way that the acceleration is a constant. And the man falls vertically. Tells us if this is the tower, which is 10 meters tall from the question, then the acceleration is equal to g, which is approximately 9.8 meters per second squared, or approximately 10. Sometimes you need to be smart to deduce your constant acceleration before you choose a suiting kinematic equation for the object. Now, from this problem, the 3 kinematic equations can be established. The first is the position function as a function of time, which is equal to the initial position. Now, the initial position, we have to be careful. It depends on where you put your 0. If you put your 0 at the foot of the tower and measure your increasing height upwards, then the initial position will be 10. Somebody can also choose to put his 0 on top of the tower. For that matter, your initial position will be 0 and your final position will be negative 10. So it depends on where you put your 0. And in this problem, it is very wise to put your 0 at the foot of the tower. So then the initial position will be 10, which will be our y0, plus u is 0 from the question because the man wasn't pushed, he just fell. So the second parameter ut goes away, it vanishes. And then the third parameter, half at squared, we have to also be careful. In other words, the constant acceleration is g. But you ask yourself, is it negative or positive? Now, in this problem, it is negative, and this is the reason. Now, you fixed your 0 at the foot of the tower, and you measured your increasing height upwards. But then you know that gravity points downwards. So if your increasing y distances is upwards and gravity points down, then g will be negative. However, in another problem, you can choose your increasing direction of y downwards and gravity points downwards, and it will be positive. But here it will be negative. Why? You chose it. You chose your increasing y direction upwards. Then if gravity points downwards, it will be a negative. Therefore, this will be a negative half times gravity. Let's pick 10. Acceleration due to gravity to be 10. And then t squared. This is what we have. So then we have y of t is equal to 10 minus 5t squared. This will help us predict the position function at every moment in time. And then if we also know the position at a point in time, we can also predict the time it will have that position. So in this problem, we can choose to use this equation to solve it. The question is, at what time does he hit the ground? Now when he hits the ground, the final position will be 0. So you put 0 here, and that will be equal to 10 minus 5t squared. So 5t squared will be equal to 10. And then making t the subject, you get square root of 2. There are two answers to this question. T is equal to square root of 2. It's either a positive or a negative. We pick the positive. But the question goes, why do we pick the positive and leave the negative? We pick the positive because negative time is in the past. So it means that if somebody was launched from the foot of the tower in the past, square root of 2 seconds in the past, with a recommended velocity, now he will land on the tower at the same time you set your clock to 0. So now t is equal to positive square root of 2. We pick the positive square root of 2 seconds. So this equation is independent of the tower. It doesn't know the tower. So it transcends both from the past to the present, then from the present to the future. Okay. We could also ask another question. What will be the velocity as it momentarily hits the ground? For that matter, we use the second equation, which is v of t is equal to ut, u is 0, so is equal to minus gt, minus because of how we chose our increasing direction of y. For that matter, that will be equal to negative g, which is 10, then times square root of 2. We have negative 10 square root of 2 meters per second. And the velocity is also negative because it is kind of coming downwards, and we chose our increasing y direction upwards. That's why we are getting the negative here. Our next in this class of advanced physics is a discussion of vectors. Stay tuned, subscribe, click on the like button and share. Please do that to make physics spread.